The question is, AES67 and SMPTE2110, now that they are released and available in the market, are they the Vulcan nerve pinch to Ravenna? Well, in order to answer these questions, we may have a very quick look on what is Ravenna. And well, you all know Ravenna is a very, very nice city in Italy. Unfortunately, it has been struck by this COVID problem, struck hard by this COVID problem. So Ravenna is on the Adriatic Sea, very, very nice town there. Just very few of you might know that there's another place in this world called Ravenna, which actually is in the Black Forest area in southwest of Germany. As you can see here on the picture, they have a wonderful Christmas market during December time, and it's a fantastic atmosphere there. So if you ever have the chance to visit that area during Christmas time or pre-Christmas time, just go there. And you know what? The best thing is they also have very precise clocks there. They have the so-called big Grandmaster cuckoo clocks, as you can see on the image in the upper left. Well, unfortunately, that's not what we want to talk about. We need to talk about basically this. How do we get lots of audio channels into a small network jack? So that is what Ravenna is, the IP-based real-time media network. And of course, Ravenna is an acronym, abbreviation, and that stands for real-time audio and video enhanced next generation network architecture. I know that some people might have heard about other stories about the name floating around, but this is the official abbreviation and name for Ravenna. So in order to answer the question, what is Ravenna, we should briefly look into why is Ravenna being invented in the first place. Well, let's have a brief look at the network audio timeline, which might be interesting as well as surprising in one or the other aspects to you. So it all started actually in 1996 when CopraNet was patented. CopraNet was a Ethernet layer 2 solution, strictly running on 100 megabit Ethernet. And its first commercial use was in 1997 during the Super Bowl halftime show. And then the first permanent residential installation was 1998 in the Disney Animal Kingdom, actually. So from there, we have a quick look into what happened on the standard side of things. The initial RTP, real-time transfer protocol standard, had been published in 1997. The number is not very often referenced these days anymore. That's because the RFC 3550 is the successor of this initial standard paper that was released in 2003, and everything we are doing these days with RTP is based on this standard. So that's one of the most important standards that have been published by the IETF, Real-Time Transport Protocol. 1999, Gibson came up with a wonderful invention, Gibson Magic. So their vision was to have guitars which are not connected with analog lines to the amplifier anymore, but which can be connected through a network jack, you know, for any sort of concurrent access, be it the recording session, the monitoring, the front of house, whatsoever. So they invented Gibson Magic, which also was a fast Ethernet layer 2 proprietary solution. Well, unfortunately, as we know, by now, these guitars never made it into the commercial field. And if you can get hold of one of those prototypes, just, you know, stick to it. Then the same year, GigaNet developed very fastly, and so the gigabit Ethernet developed very fast, and the gigabit Ethernet standard had been invented. So we increased the speed from 100 megabit to 1 gigabit, 1000 megabit per second. In 2001, another Ethernet, fast Ethernet solution entered the market space. EtherSound, very well known in the live field. And then in 2002, we already saw the inauguration of the first precision time protocol standard, PTP version 1, or officially known as IEEE 1588. All right. In 2003, the first IP-based audio transport solution entered the market. There was the Livewire from our friends at Telos Alliance. They invented the Livewire and ran it as the Axia system. This has grown a very, very popular system among radio stations in the US and some Asia Pacific regions. But that was the first purely IP or layer 3 based audio distribution system. Then in 2006, the well-known Dante system entered the market space. As we all know, Dante has a very, very large footprint in the market. They are mainly targeting the live and commercial install sound areas, and they are basically built on layer 3 protocols, although most of their protocols and technology is proprietary, but is still based on certain standards. Then in 2007, the EBU, the European Broadcasting Union, defined the ASIP standard for contribution and distribution of audio content through, the internet or any other not so stable and not so performant connection line. So basically for journalists sitting somewhere in a field and contributing their audio signal to the radio station through dial-up lines, anything and other wacky lines. This is also a layer 3 technology. So then in 2008, the Ravenna R&D team has been created. So 2008, when we sat together, initially we had the vision of a platform-independent content exchange technology. And of course, we nailed down some requirements. And these requirements originated from the very, very strict requirements of broadcast. So we were originating from the broadcast side of things. And some of these requirements you can see listed on the left side. So we definitely needed to have a very, very fast and scalable solution, and very flexible in terms of signal adoption as well as of size of systems to be built on that. And we also wanted to have a non-proprietary solution based on standards. And when developers sit together, they always take out sheets of paper and start to scribble something. And some of you might have seen this. This is our first initial draft of how we would see the application for a thing which at that time wasn't called Ravenna yet, but was envisioned to be the IP-based transport technology, which could connect between the production side of things, where you have latency requirements of less than 2 milliseconds between any devices, and then the wild world out there, which is based on IP, where you can distribute signals back and forth. And ideally, it was not just the exchange technology for the wild IP world with the production world, but could also be applied to within the production environment. So that was the initial idea of what we wanted to achieve. And then we looked into the topic, because we were all coming from the audio side of things, and we're just, not so knowledgeable at that time about what was going on in the networking side of things. So we looked in all to these different things and discovered a lot of acronyms and buzzwords, and came across existing technologies and solutions and requirements. And what it all created was confusion at the first place. So what we had to do, we had to clearly dive into this confusion and see what is really available, what technologies are applicable, what is available on the market. Maybe just take something from the market before we invent the wheel twice. So market evaluation and technology assessments were among our very initial steps before we were inventing anything in this direction. And it was immediately clear, whatever we do, it had to be based on IP, so on layer 3 instead of layer 2. We were, of course, aware of these Ether Sound and Copernet and these solutions, but they were all based on layer 2, and layer 2 lacks the ability of transport signals or packets across different network segments or wide area network connections, because it's limited to a local area network. So IP was the solution, and we saw the telco companies just building or rebuilding all their networks from circuit-driven installations into packet-based, into IP technology. So for us, that was the right step to go, the right direction to go. And then finally, the question was, take something existing or do we have to make it on our own? So again, we were diving into the available technologies and evaluated the at that time existing audio over IP solutions. So we of course came across the Livewire technology, as I already mentioned, from Telos Axia. WeetNet was there, Dante was visible, introduced in 2006, the NESIP scheme was visible, and we also had a very close eye on audio video bridging, AVB. Although we knew, of course, that this is a layer 2 solutions, they promised that they would provide some bridging into layer 3 world as well. So we had a very close look at AVB at that time. So then we did a technology evaluation, and against our requirements we had set forth at the very beginning, and we found that some were close, but not as close as we wanted them. Some were just not qualifying technology-wise. Others were a perfect match. As you can see, the Dante has a green smiley here, so the technology platform provided by Dante was able to satisfy our requirement criteria, and AVB as well, although with a layer 2 approach, we were not sure if this would ever go into layer 3 at all. So then that was the technical side of things, and then we evaluated the commercial side of things. And by looking at that one, we found that, well, those who were open technology, based on open technology, were not so suitable on the technical side of things, and those suitable on the technical side of things, well, were not open technology. And so the decision we had to take is, do we have to rely on something where we don't have our hands on, where we can't require performance enhancements or whatever, and buy something from somebody, and we just don't know what actually is in there and how it will develop, or do we have to do it on our own? And the decision at the end, of course, was we have to make it our own, because we wanted to have full control on how things are evolving and needed to address changing requirements of the critical broadcast application market into this to be developed technology. So make was the decision. And so in 2008, we started the whole process, and the development started late in 2008. And in 2009, we already introduced our prototype developments, the whole idea, the whole concept of Ravenna, to some selected industry partners who joined us in our efforts, so that in 2010, we were able to publicly introduce Ravenna at the IBC 2010, and already had some working prototypes in this initial prototype setup. Some may remember this big green wall at the Lavo booth, actually, where we already had Lavo gear. We had Ganalex speakers in there. We had contributions from Meinberg. And so that was quite a nice introduction of the Ravenna technology back in 2010. Oh, and yes, we have 2020 now. So that means that this year, Ravenna is celebrating its 10th anniversary. And if IBC is going to happen, we definitely will have a big party in Amsterdam. So let's come back to what Ravenna actually is. Once we have looked at the history and the why Ravenna is there, I always describe Ravenna as being an open technology platform. We understand that this is identified by a few characteristics. First of all, it's based on technology which is publicly available. So Ravenna does not incorporate any proprietary black box components. It fully utilizes standard protocols which are widely supported. It is designed to work on existing networks, because we were absolutely clear from the very beginning, if we want to get this into broadcast environments where they already have large IP-based networks in place, we can't require them to build individual separated networks just to transport time-critical audio on them. So it had to work on existing network infrastructures. We didn't go down the road of licensing, so we decided to make it an open, licensing-free technology. There is no cost per channel or per device or whatever involved. Everybody who wants to build Ravenna can do it without paying any licensing fees to anyone. And then we finally published the draft of operating principles of Ravenna, so that everybody can actually read how Ravenna is architectured, how it works, what protocols are employed, and what needs to be in place to actually build a Ravenna implementation. So you can see the operational draft like a cookbook. Well, a cookbook has a list of ingredients, as you can read here. We need a bit of precision time protocol, RTP multicast, bonjour, and a few more ingredients, of course. Every good cookbook also has a cooking order. And that's the cooking order, and that is also part of the Ravenna draft and operational principle. It doesn't give you a very explicit construction plan so that every Ravenna implementation looks just the same as another one. So compared to cooking recipes, you can have a tomato soup, but that tomato soup can be a hot one, a blank one, a red one, a green one, but it's still tomato soup. And that's the way for Ravenna. We wanted to keep it open so that people can cook their own extensions, their own flavoring of Ravenna, but at the end, it all had to be Ravenna. So, and of course, that is still available on the Ravenna website. So, since that was open throughout the time, we saw quite a lot of companies joining us and joining forces in implementing Ravenna into products and into projects and applications. So here's just a quick list of current Ravenna partners and supporters. These were the 5 initial companies contributing to Ravenna, and then some 40+ companies joined us and came in over the last 10 years. As you can see, most of them have their core business on the broadcast side of things, but there are just also a few who are working in the recording or install sound area. So, and let's summarize the key features quickly, not to go into technology details here at the moment. First of all, Ravenna is a fully layer 3 built solution, and thus it can operate on the existing network infrastructures. It doesn't need to be set aside or have any particular special network infrastructure devices in place. One of the requirements was phase accurate distribution of media clock. For some of you, AES11. That's the standard behind it. We wanted to have full bit transparency with all media formats, so no sample rate conversion. What goes into the network has to come out absolutely bit replicated on the other side of the network. And we also needed to have support for multiple media clocks and data formats, which is what Ravenna can offer. Lowest latencies are supported for real-time critical applications. By now, we even can run MADI-like streams in a MADI performance across the Ravenna network, given, of course, that the network infrastructure can cope with the massive amount of packet data. And the capacity, because it's based on layer 3, scales with the underlying network infrastructure. So we are not limited to 100 megabit or 1 gigabit, or if we go to 10 gigabit or even 100 gigabit, which is available in backbone infrastructures these days. We don't have to change anything for Ravenna at all. It simply scales and uses the increased available bandwidth. Since it's layer 3, distribution and synchronization across network segments, even across cities, is possible. So you can actually have synchronized streaming between, let's say, Frankfurt and New York. If you have the correct infrastructure in place, the matching infrastructure in place, and full network redundancy is also, although just an optional part, but is also part of the Ravenna definition. So if you want to go for full network redundancy, that can be done with Ravenna as well. And everything is based on standards and it's open technology, as just explained a few slides earlier. So that's about the key features. Let's go back to the timeline. So we have 2010 when we introduced Ravenna to the public. Just shortly after that, there was a work group initiated in the AES. It's called the AES612 work group, which is basically the work group which came out with the AES67 standard. 2011, AVB Ethernet extensions were then finally published and available, but no word about layer 3 connectivity there. And finally, AES67 was published in 2013. So let's have a quick look into this very, very important standard, AES67. What was the motivation? Well, we had these different IP-based solutions, which you can see on the top. They were all based on IP, but they were not able to natively talk to each other based on IP. So you had to go through analog or digital signal conversion in order to transport signals from a, let's say, Ravenna to Dante network or Livewire and Ravenna. Well, which is not quite true, because already back in 2012, the engineers from Axia and we sit together in a room and we came up with a solution on how to actually integrate the new LiveWire nodes as well as the legacy LiveWire nodes into a Ravenna network. And so we were already able to exchange streams based on IP without having to go through the analog or digital domain back in 2002, but for 2012. But for all the other solutions out there, AES67 was the cure, because with AES67, if it would be supported by the individual solutions, it would have been able to actually transport signals on the IP domain. And as we know by now, because of this history, all of these solutions do support AES67, so it's possible to interchange signals or streams directly on the IP layer without having to go through analog or digital. So without going into details, this is more for the upcoming presentations, but in order to actually establish something like AES67, you need to define or identify a number of functional blocks, like those on the left side, goes from synchronization, transport, encoding, all the way up to connection management. And you have to define some common ground or some commonalities which would have to be supported by all these different technologies in order to make exchange based on AES67 happen. As we all know now, precision time protocol was in the game. Things like, L24, 48 samples per packet, 1 to 8 channels, and so forth. All this has been defined by AES67 in order to make the interchange possible. And details of this will follow in, as I said, one of our upcoming webinars. What hasn't been part of AES67, deliberately not being part of AES67, is the whole scheme of discovery. Discovery has not been specified to be part of the AES67 suite, because actually to do a technical interchange, everything below is required, but just not the discovery. So you can look at discovery just like at the phone book, which would tell you who is available under which particular number. But even if you don't have the phone book available, if you know the number of somebody you want to call, you can do the call, you can establish the call. And that's actually what is AES67 about. It's covering everything you need to have in place to actually make a successful connection to the other side, and it doesn't require any particular discovery method. Okay, so the question then is, how does AES67 relate to Ravenna? Let's look at this like in this example. AES67 is specifying a number of mandatory requirements in various functional areas to be AES67 compliant. And it turned out when AES67 had been released or published, that everything which was required by AES67 was in place in Ravenna anyway, but Ravenna would offer much more variability or flexibility in any of those functional blocks. So we had the choice of more sample rates to be supported, different packets, different channel support, and so on. And Ravenna was offering more functionality than actually been specified in AES67, just like redundancy and discovery, which I just mentioned, is not part of AES67. So from the perspective of Ravenna, AES67 is fully built in as a particular operating profile, or you may call it stream setup. But it offers more options and more features which go beyond the requirements of AES67. Or to make it a very simple picture here, Ravenna AES67 built in, it's the big brother of the AES67 child. Okay, back to the timeline. So AES67 had been published in 2013. Ravenna was immediately natively compatible to AES67. And then, of course, the first Ravenna OEM boards were coming from Artwave, actually. A low channel count board was there. ALC Networks, our company, released a high channel, high performance OEM board 2014. Telos then announced AES67 support for their newly created LiveWire Plus scheme, which is backward compatible to LiveWire as well. Ravenna had been used successfully used in all 12 soccer World Cup stadiums in 2014 as a commentary system. And in 2015, it had been used for the European Song Contest with 6,600 audio channels being transported across Ravenna technology in this live event. In 2015, we saw a revision of AES67. Nothing new actually appeared here. We were just doing some, removing some ambiguities, some error correction, clarifying some wording. So that revision was not doing any change to the original 2015 release in terms of functionality or requirements. Then 1 year later, Ravenna was used for the Rio Olympics and the European Soccer Championships. So every audio signal you were listening to during the European Soccer Championship were coming or running across a Ravenna line somewhere in France. QSC announced AES67 compatibility, and also finally Ordinate announced that they would support AES67 for the sake of interoperability at the end of 2016, and it came up in 2017. 2017 saw a very interesting year for Ravenna as well. We got the first international award assigned. That was for the Hamburg Elbphilharmonie, where a full Ravenna installation was is of course being used for transporting all the signals in the two big orchestra areas. And the interesting thing here is they have actually two host production companies in the house. One is the public radio station, Hamburg Public Radio Station, Norddeutscher Rundfunk, and the other is the host operator inside Elbphilharmonie. They are using the very same network, the very same sources, and the whole system has an included access rights management system, so that they can't, even if they are using the same sources at the same time, they can't disturb each other when working on those signals. And then, end of 2017, another very important standard had been published, the SMPTE ST2110. So let's have a brief look into SMPTE 2110, which is called Professional Media over Managed IP Networks. Well, up to now, remember, Ravenna AES67 focusing on audio, and 2110 now includes actually video. So 2110 is a standard which specifies the transport, synchronization, and of course description of separate elementary essence streams like video, audio, and story data over managed IP networks. So again, this is not the internet. It's fully controlled, manageable production networks at any speed for, and that's the purpose, real-time production, player, and other professional media applications. So in order to understand what 2110 is, how 2110 is different to already existing video over IP standards, we have a quick look at the SMPTE ST2110-6, which is the SDI over IP standard. Now we call this the bundled approach. If you look at an SDI signal, you have the active image area with all the nice colorful pixels in there. We have the bank and the hang data space, and the audio is part of this space. So we have all these signals basically as a combined multiplexed SDI signals packetized into one packet stream. So at the end, the IP stream, which is being transported on the network, has the multiplexed AV and metadata signal in it. So it's one stream with this signals multiplexed in it. Now, 2110 takes the essence-based approach. So we still have the same ingredients, but now they are transported as individual essence streams living on the network as individual RTP streams. So active video is one of those essence streams. Any number of audio channels is another type of essence on the network with its own stream. And then we also have the remaining ancillary data, SDI ancillary data, which is another type of stream on the network. So what's the benefit actually of having this approach compared to the 2022-6 approach? Now let's have a look at 2022-6. Let's assume as part of the whole production task, we have an audio processing unit, a mixer, for example. Now, in order for the mixer to access the audio data and process the data and put it back onto the network, it has to subscribe to the full 2022-6 stream, including the video, de-embed the audio data only, do the audio processing, and reform another 2022-6 stream with the video data in it. So it has to do a lot of bandwidth. It has to offer a lot of bandwidth and to do a lot of processing to just get hold of the audio data. In 2021-10, we have these streams already living as individual essence streams on the network. So the audio processor, the DICs, the mixing desk, does not have to do any de-embedding or re-embedding. It just subscribes to the audio stream, does whatever it has to do, and initiates or generates another audio stream, puts it back on the network. So that is the basic difference. So it's a lot of taking away a lot of processing and bandwidth power to individual devices on the network. So let's have a quick look into the 2110 standard. There's the document structure. Actually, it's not just one document. It would just be a very large document. So we have structured 2110 into different documents. There's the -10 document, which covers all the system timing and definitions, defines the transport layer, how the synchronization is done. Those are mainly based on IEEE standards, IETF standards. We have the -20, which is describing how uncompressed active video, so the active video pixels, are transported utilizing RTP. That relates back to an existing IETF standard, the RFC 4175. Then we have the -21 document, which describes how senders who are putting -20 streams on the network have to behave timing-wise. Because you can imagine that with uncompressed active video, there's quite a lot of data immersed into the network. And so the senders have to do it with some sort of traffic shaping in order not to overload any subsequent switch or receiver stages. So all this is described in 21. This is not applicable to audio because audio compared to video is just very, very small data, and there's very rarely or seldom the case that audio may overload subsequent buffer stages. Just newly published is the -22 standard, which talks about how to packetize compressed active video with constant bitrate codecs into an RTP stream. It does not define the codec itself, so there's still the choice of using J2K, JPEG-XS, VC2, and any other codec which might be out there, which is constant bitrate. It just describes how this is packetized into an RTP stream and how it relates back to the timing described in -10. So on the other side of things, there's the -30 standard, which describes how PCM digital audio is being transported. That relates to the AES67 standard. We have the -31 standard, which describes how AES3 transparent transport is done. PCM is just L24 audio, but AES3 has additional metadata as being defined by the AES3 standard, which also provides the ability to transport other formats than just linear audio, just like nonlinear audio or other data formats across the network. And then we have the -40 standard, which covers the transport of the SDI ancillary data, which is not the active video and not the audio. Okay, let's have a quick look at the audio side of things, because that is important when we look at the relationship of Ravenna again. So that's the -10, the -30, and the -31 document from the standard, which cover audio transport. So let's look at linear PCM audio first, -10 as the system document and -30 as the payload format. And we can make a very easy and a shortcut at this point. We can say everything which is described in here in terms of audio is already described in AES67. So basically, the standard could say, just refer back to AES67 and you're done. Well, however, SMPTE did add some constraints to their -30 and -10 documents. So we have to be careful as an implementer, particularly of AES67 devices. If you want to be 2110 compliant, you have to be aware of those constraints and make sure that those constraints are met by your implementation. Those who are interested in those constraints and details should follow one of our upcoming seminars, of course, or just go to the AIMS website and download a white paper on those commonalities and constraints, which describe nicely what these constraints of 2110 with respect to AES67 are. Not going to any details here, just giving you a quick overview picture. So we have AES67 with its mandatory requirements and optional possibilities. And part of this is the SMPTE 2110 specification, but it has some constraints, in terms of timing, operational constraints, and something I won't describe in detail at this point here, but the baseline is 2110-30 level A is fully in line with what AES67 covers. And then there's a level B definition. This is also covered by the optional configuration parameters described in the AES67 standard. And back to Ravenna, of course. Ravenna covers it all. So everything which is defined in 2110 is already part of the Ravenna framework and definitions. So that's why we added them now with ST2110 3 years ago to our logo. So let's have a quick look at the AES3 bit transparent audio data transport. And remember, L24 linear PCM, and then we have the additional metadata bits defined for AES3, so that it enables you to transport anything basically which can be transported within an AES3 line or through a MADI line, which is of course the metadata bits, but also non-PCM audio formats like Dolby E and other formats specified by another SMPTE standard. So what we have to do actually, we had this already defined in Ravenna. Ravenna had this ability from the very beginning, because when we worked the list of requirements, that was an imminent requirement to transport AES3 bit transparently. So Ravenna had this already in place, and we called it AMA24 at that time, which goes back to the standard, to another standard actually. So what it does, it retains the whole AES67 definition for synchronization and RTP usage, but it adds 1 byte of payload to the data format. So we have the L24 payload data, but we also have an additional data byte which carries the PCUV and the block and frame start bits. That's the simple secret behind AES3 transport on IP networks. Everything else stays the same. It's just the signaling and the transport which makes the difference actually. So all the other SDP parameters and all the other definitions stay in place. So adoption of Ravenna's AMA24 or -31 format is very easy for manufacturers. And we have a nice initial application for this. As an example, during last IBC, we had a joint demonstration with Dolby. So what they were doing is they had an audio playout of 5.1 plus 3 language channels, different language channels like English, Mandarin, and Hindu, sitting on two just too quick on my mouse button. Sitting on AES67 streams, so that was pure AES67 streams containing these signals. But then we had a metadata authoring tool, which was generating serial ADM data, which can be transported by AES3 because it's defined in SMPTE So what we did, we were actually converting this into a -31 stream using the Ravenna AMA24 format. And then the renderer could receive the linear audio streams, the 9 different channels, and by looking at the incoming SADM metadata, describing metadata streams, it was able to actually render what the author wanted to be played back at the moment. So let's say the 5.1 rendered onto a 2.0 installation with the Hindu language switched on. So that has been demonstrated, and it was utilizing these standard transport definitions. So let's have a quick look at the audio compatibility. How are AES67 and 2110 compatible with each other? So I already mentioned that if we look at -30 and AES67, AES67 is a larger definition, but there are some constraints which lie outside of AES67. So these have been known to AES67 implementers in order to be fully -30 compliant. And if we look at the stream compatibility, so how do AES67 and -30 streams compare to each other? Well, every -30 stream can immediately be taken up by any AES67 implementation. However, an AES67 stream need to obey the few constraints which are set forth in -30. But I can tell as of now, basically every AES67 implementation has adjusted to match these particular constraints. So any AES67 implementation out there should be -30 compatible at this point in time. For AES3, we have the -31 standard, and AES67 is not part of the game anymore because that's not covered by AES67, but Ravenna incorporates all of the ingredients of the -31 standard. So looking at the streams, AES67 again is not part of it, but Ravenna is in any Ravenna stream formatted according to the 2110 profile, can immediately be taken up by the -31 implementation, and vice versa. Although to be fully Ravenna compliant in every aspect, a device would have to add the additional functions defined by Ravenna, like discovery. But even without discovery, the connection is possible under any means. Okay, so that brings us to the summary. Why would one use or choose to work with Ravenna? It's the flexibility, because it can accommodate a wide range of formats and rates packet times. Any channel bundles are possible with the streams. The performance is one of the key features. We have full bit transparency. The capacity scales without any technology change, and ultra low latencies are possible, just like MADI over IP. It's fully open technology. It can be enhanced, expanded by the manufacturers as they desire it. We have examples by merging technology who also transport DXD, DSD streams at 384 kilohertz across the Ravenna infrastructure. There's no licensing in place, and there are various OEM providers where you can buy ready-made SOM boards from if you don't want to do your own implementation. It's fully based on existing standards, so it works nicely within managed IT networks. So it's the IT admin's nice baby. And since the whole Ravenna architecture is very, very modular and layered, it can immediately adopt to any emerging standards and technologies out there. And proof of that concept has been the full compatibility with AES67 and 2110 without needing to change anything in the Ravenna standard at all. And also the uptake or the adoption of the session announcement protocol, SIP protocol, ST2059 timing definitions, the redundancy scheme set forward by the SMPTE, and of course, the emerging NMOS functionalities, which can all be added. They are not part of the Ravenna core definition, but they can all be added to a Ravenna implementation without interfering or harming any of the existing implementation schemes. So, and finally, all this makes Ravenna the most prevalent technology in broadcast applications. I know this is all complex stuff. It's not a get me a board, plug it in, and everything will work. You need to have a bit more of understanding how networks work, how networks have to be structured. But then Ravenna offers you a very, very rich possibility, feature set, and adaptability to any upcoming application requirements. So finally, the question to be answered is, are AES67 and SMPTE2110 the Vulcan nerve pinch to Ravenna? Here's the answer.
Illogical. Fascinating. Live long and prosper.
And as you can see, we have 10 years behind us, and I hope there are many, many more years to come. So that brings us to the end of the presentation. I thank everybody who been with us online. And well, any questions can be sent later on, of course, through email or the webpage contact form. Yeah, I'm happy to answer all of your questions, and we got quite some time left for QA at this time. Roland, are you with us?
Yes, thank you, Andreas. That was a great presentation. Thank you very much. Very informative.